Hey, welcome. Today we're going to crack a secret code. And no, not one that spies use, but one that's hidden right inside of math. It's this simple, really elegant language that helps us describe some of the most powerful forces out there. That kind of explosive, rapid growth. So let's get into it and crack this code together.
All right, so let's dive right in with a calculation that seems super easy at first, but you'll see pretty quickly how it becomes a real headache. Okay, so take a look at this. We start with 5, we multiply by 2, we get 10, we multiply by 2 again, that's 20, and one more time, that gives us 40. Simple enough, right? We can all do that in our heads. No problem at all.
But hang on, what if we had to do that 20 times? Can you imagine trying to write out 5 times 2 times 2 times 2 over and over again? It's just so clumsy. It would take up a ton of space, and you just know you'd lose count somewhere along the way. There has to be a better way to do this.
So, to find that better way, let's switch gears and try thinking about this visually. We're going to look at our really simple pattern of circles that grows in a very specific and, as you'll see, a very powerful way. So, check out this pattern. At stage 0, we've just got one circle. Then at stage 1, we have 2. At stage 2, it jumps all the way to 4 and then to 8. Are you seeing what's happening? With every single step we take, the number of circles is just doubling. So if we're following that logic, just take a second here. We know stage 4 has 16 circles, and we know the pattern is doubling. So what's next? What do we get for stage 5? Exactly, 32. We just take the 16 from the stage before and we double it. The pattern is super consistent, it's predictable. But we're about to hit that same wall again. Because, sure, what about stage 12? I mean, yeah, we could keep going. 32 becomes 64, then 128, but it's getting tedious, isn't it? We are right back where we started with that first problem. And this is exactly why we need that secret code. And this brings us to this amazing breakthrough moment, which was actually discovered by 2 students, Ada and Jamal. They were looking at this exact same problem, and their 2 very different ways of solving it gave us that aha moment we've been looking for.
And here is the solution, right here, side by side. On the left, you can see Ada's approach. She wrote out the full multiplication, 2 times itself 12 separate times. It's totally correct, but man, that is a lot of work. Now look at Jamal's way on the right. He used this incredible shorthand, a big 2 with a little 12 written up above it. This is our code.
This special notation, it's called an exponent. The big number on the bottom, the 2 in this case, is what we call our base. That's the number we're multiplying over and over. And that small number up top, the 12, that's the exponent. It's just an instruction. It tells us how many times to multiply the base by itself. It is a super compact and really powerful way to write all this out.
So here's the bottom line. Both Ada's really long calculation and Jamal's elegant 2 to the power of 12 get you to the exact same massive number, 4,096 circles. So the real question is, which way would you rather write it down?
Okay, so we've cracked the code. Now let's really put it to the test with a brand new pattern and see this thing in action. So this time, instead of doubling, our pattern is going to triple at each stage. So right away, you know the base of our multiplication won't be 2 anymore, it's going to be 3. All right, here's a new challenge for you. We're at stage 5, and it has 243 circles. We need to figure out stage 7, which means we have to triple this number 2 more times. So how could we write that using our new code? And I'll give you a hint. There might be more than one right answer here. So it turns out all 3 of these work. 3 to the power of 7 represents the whole calculation from the very beginning. But we can also just start at stage 5 with our 243 circles and multiply by 3 and then by 3 again. And since multiplying by 3 twice is the same thing as multiplying by 3 to the power of 2, that expression works too. It just shows you how flexible this code really is. So by now, we get how exponents work, but it's just as important to know when to use them. You see, they aren't for every problem, but for one very specific job, they are the absolute perfect tool. And here it is, the key distinction. Exponents are only a shorthand for repeated multiplication. So 7 times 7 times 7, that becomes a nice clean 7 to the power of 5. But for repeated addition, like adding 10 to itself 5 times, we don't use exponents. That's just regular multiplication, 5 times 10. Knowing that difference is absolutely everything. So let's just boil this all down. What did we learn today? First, exponents are our secret code for repeated multiplication. Second, they're the perfect language for describing that explosive kind of growth. And third, they turn these impossibly huge calculations into something that's actually clean and manageable.
And that brings us to our final thought. This is not just some math trick. It really is a new lens for seeing the world. Think about a viral video spreading online, or the growth of bacteria, or even compound interest in a savings account. Now that you know the language, what patterns of exponential growth are you going to start to notice?